All right, hopefully this is in focus. Is the camera counting? Is it moving? All right, so welcome to Math 150, Section 2. Is it out of focus? Or? I'm sorry?
It needs to go that way.
Okay, it needs to go that way. Okay. Is it that way now? Oh, it needs to go towards this way. All right. Is that good? Yep. All right, excellent. Welcome to Math 150, Section 2, Lecture 10, Method of Least Squares. All right, so what I want to start off with is some general theory, and then we'll talk about applications, and then we'll end with a game. So how many of you have taken a stats class? Okay. So part of this is an introduction to statistics and just try to encourage you to take stats classes. So this is a very bad picture. Why is this a bad picture? No axes labels. How many of you ever read XKCD? There's a great XKCD strip where someone goes up to their significant other and says, I've done the analysis, we don't belong together, we should break up. And their significant other looks at the analysis and goes, you're right. And you go, I thought it would convince you. No. You didn't label your axes. I can do better. It is extremely important to label your axes. If the axes aren't labeled, it's very tough to know what's going on. Spring test, am I talking about maybe the weather in Williamstown, and will we actually have spring weather, or will we be fluctuating? No. This is physics spring. So how many of you remember the force law for a spring? All right, what's the force law for a spring in the back? What equals negative kx? The force. So the force is proportional to the displacement, and the proportionality constant is different for different springs. So this is fake data. So I let my displacements be 5 plus 0.2n, and I took yn to be 5 times xn plus an error randomly drawn from a Gaussian. So if everything was perfect, I should see force is equal to 5 times the displacement. But it's not perfect, there's some Gaussian error. If you look at this, does it look roughly like there's a constant of 5? How would you estimate the slope? Well, one thing's fine best fit, but without doing the best fit, how could I estimate the slope? I've got this data here. Get points from either end. So all the way, let's add 20 around 100, 0 around 0. So it looks like maybe the rise over run is maybe 100 over 20 or 5. So a slope of 5 seems reasonable. So when we use the method of least squares, we're going to get a best fit line of 4.99x plus 0.48. So that means a slope of 4.99 and an intercept of 0.48. What should the slope be, and what should the intercept be if I tell you y was supposed to be 5x? So what should the slope have been? 5. We get 4.99. Not bad. The intercept should be what? 0. And we get? Is that good or bad? I'm not thrilled with that 0.48. Doesn't look that great to me. If you had to get one thing right, which would you rather get, the slope or the intercept? The slope. As you get larger and larger values of x, the intercept is going to have a smaller and smaller impact on the actual value. So if I had to get just one thing right, we're at least getting the correct one right. All right, so what I want to do now is I want to talk about the theory of finding these best fit lines. Now, initially, you might think this is extremely restrictive to focus on the best fit lines, because most relationships in life are not linear. If you study more for an exam or for a class, will you do better? Hopefully, yes. Hopefully studying does work. I strongly encourage studying. Do you think it's a linear relationship? No. If you keep studying for a certain amount of hours, you're not going to get 120% on the exam. Right? You will definitely reach a point of diminishing returns. You might also have very high returns in the beginning. If you look at Newton's law of gravity, the force is proportional to the reciprocal of the distance squared. Most relationships in life are not linear. So I'm now going to drive home how much I love finding best fit lines after telling you that most relationships aren't linear. Unfortunately, there are two ways around these issues. And so I will then try to go through and show you why, even though we're only doing things for lines, it's not as restrictive as you might think. Am I in focus here? Excellent. So I believe y equals ax plus b, and I observe yn equals I observe yn at xn. So I have some data. x1, x2, x3, x4, these are my observation points, and I observe y1, y2, y3, y4. And I want to find the best fit values of a and b. So here is my first way to measure error. The error is going to be the sum, n goes from 1 to big N, so I'm going to go over all my data points, and I'm going to look at what I observe, and I'm going to subtract what I predicted. And so I'm going to basically just sum the errors. Does this seem like a good way to count error? For each observation, see what the error is, and then sum all the errors. Or is there an issue with this notion of error? Any issues with this notion of error? So let's imagine I give you two data points right here. What's the best fit line between them? So I see a lot of people going straight like this. And what would the error be? What's the error? 0. 2 points determine the line. You can do a perfect job. However, and remember, I'm also the person who thought that 12 over 24 equals 1/4. I think that's the best fit line between the two. And if you look, my error over here cancels my error over here. One of them is a positive error, one of them is a negative error. The two errors cancel, and I have 0 net error. There is no way in hell we should consider this the best fit straight line. That's the problem with this notion of error. It allows errors to cancel. Well, I made this mistake and I made that mistake, but they cancel out now, and I'm now no longer in trouble. No. Okay. How could we fix this and have the errors not cancel? I'm sorry? We could square. So I'm going to put that down here as the third choice, so that the notation is consistent with the earlier class. So yn minus an plus b, I'm sorry, anx, sorry, minus axn plus b squared. And by squaring it, now you have sums of non-negative things. Great. What else could we have done? Absolute values. So it would be the sum, n goes from 1 to n, of the absolute value of yn minus axn plus b. All right. We should all agree that the first notion of error is right up. It is not worthy of being considered. But we have two valid candidates, E2 and E3, absolute values and squares. But in this class, one of them is a significantly better choice than the other. And the hint is in the name of this class. So, anybody know why one of them is better and which one is better?
The third one is better because we're learning about least squares.
Oh, well, okay, that's the title of the lecture. Okay, so you're right. You can take class 2 as the title of the course. The course title. What is the course title? Multivariable calculus. What's the difference between E2 and E3? Should have something to do with calculus. This is a calculus course. I should be doing calculus at some point. I can differentiate the square function. I can't differentiate the absolute value function. Does that mean this is a bad notion of error? No, it just means the tools of calculus are not available. The way I like to phrase it is, if I'm hiring someone, I want them to use the absolute value. If I'm being hired, I like to use the squares, because then I can use calculus and I can have a closed form solution for the error. So I can have a closed form solution for the best fit parameters A and B. But the fact that the absolute value function, it's differentiable everywhere, but at one point, is that really that bad? Yes. That one point where it's not differentiable means I can't get a closed form solution for the best A and B by using these squares. I have to use numerical techniques. You can do it, but it's not as easy. We will see there's an explicit formula for the best fit parameters A and B using calculus. So the goal is find A and B to minimize the error. How do we find the A and B that will minimize the error? What do we do? Yes? Take the derivative, find the critical points. Okay, so we find the critical points. And check the endpoints and check the boundary. Right? I don't want to bother that class again. Can't do it too often. I don't really want to go right into the glass. Right? You must check the endpoints. Now, in multivariable calculus, the endpoints mean the boundary. What's the boundary here? Well, A and B are going off to infinity. What do you think happens to the error as either A or B go off to infinity? It's going to go off to what? What's the error going to go to as A or B go to infinity? Sorry? It's going to go to infinity. Imagine A is fixed and B goes off to infinity. Then this difference is going to look like negative infinity. I'm going to square it. It's going to become positive infinity. So if either A or B is going off to infinity, it's clearly not going to be the best fit line. Another way of looking at this is I have a finite set of data. It's contained in a finite region in the plane. If either A or B or both are going off to infinity, I'm nowhere near my data. It's going to be bad. So whatever value of A and B gives us the smallest error will be the A and B we want. The critical point will be the one we want. It may not be a good fit. If I give you a set of data which is not even close to linear, I can still find the best fit line. The best fit line may suck, but I can find it.
Is that why when you are looking to find expected values and whatnot, you can't extrapolate because the error is still?
No. Expected values is something different. We can talk about that. The expected values also don't always have to exist for probability distribution. So there are some issues there. All right, so we're all agreed we're going to look for critical points. All right, so I will now try to shift the camera. All right, so we want 0 to be the derivative of E with respect to A, and we want 0 to be the derivative of E with respect to B. So we need to take these derivatives. Well, if you look at our formula, the derivative of a sum is the sum of the derivatives. And this is going to allow me to review some summation notation, which we're going to need when we get to what is the area under a surface. This is the multivariable calculus analog of what's the area under a curve. I guess what's the volume under a surface. So we are going to need to use the summation notation later. So while I love this topic, it's not entirely coincidental that we're doing this. It's a way to review things we're going to need later in the semester. So the derivative of the sum is the sum of the derivatives. And then I have this y minus axn plus b squared. So I'm going to have a 2 come down. I'll then have this whole expression. Then I take the derivative of this expression with respect to a. What's the derivative of this expression with respect to a? I'm sorry? Not negative n, negative xn. So what's a little bit confusing is xn and yn are not variables. They're fixed, they're observed. And when I take the derivative with respect to a, I get back a negative xn. So I can pull out the negative sign, I can pull out the 2, and I'll get negative 2, the sum, n goes from 1 to n, of yn minus a xn minus b times xn. So all the algebra I'm doing now is in the handout that is posted online. So if you don't want to write down the algebra now, if you just want to enjoy the unfolding of the equations, by all means go for it. Right? Any questions on how we got this derivative? So now we do the same for the other ones. We'll get a negative 2. The sum n goes from 1 to n, yn minus a, xn minus b. And now we take the derivative of this expression with respect to b. What do we get when we differentiate with respect to b? We got negative 1. So I already put out the negative sign, so I just have a 1 over here. All right, so now what I'm going to do is I'm going to just write this in a more compact notation. Now, I will get the sum, n goes from 1 to n, of xn, yn. That's this piece. I'm dropping the negative 2's. Is it okay to drop the negative 2's? Yeah, it equals 0, right? So I can drop the negative 2's. So I get the sum of xn, yn minus the sum of a, xn, xn. I'm just using the sum of a difference as the difference of the sums. But in all the terms here, I have a, xn, xn. A doesn't depend on n. If I multiply every term in a sum by 5, it's the same as just multiplying the sum by 5. So I can pull the a out. So it's going to be minus a, the sum, n goes from 1 to n, of xn squared, minus b, the sum, n goes from 1 to n, of xn. And this is supposed to equal 0. So any questions as to how I got this? So now we do the same for the other one. We get the sum, n goes from 1 to n, of yn, minus a, the sum, n goes from 1 to n, of xn, minus b, the sum, n goes from 1 to n, of 1, equals 0. So as the equations get more and more involved, it's worthwhile to occasionally just take a moment, pause, and try to remind yourself, what the hell is our goal? What are we looking for? What are we trying to find? Okay. So what are we looking for? What are we trying to find? I'm sorry? We're trying to find A and B. So the goal is find A and B. When we look at all of this, it can be confusing. For example, if I give you f of x equals x times the natural log of 5, how would I take the derivative of x times the natural log of 5? What rule of differentiation would I use? 2 answers are fine. I'm sorry? Product rule. What else could I use? I could use the constant rule. What's the derivative of 7x? What's the derivative of 13x? The natural log of 5 is a number. What is the derivative of the natural log of x times the natural log of 5? It's just the log of 5. But when you see the log of 5, a lot of people don't pass that as a number. And you might think, well, let me use the product rule. It is not wrong to use the product rule. But it's not the fastest way either. And it's very easy to be confused as to what is varying and what is fixed. So I'm going to just put these things in parentheses to remind myself that these are all numbers. And the A and the B, those are the only things that are truly free. I have 2 equations and 2 unknowns. We know how to solve that. This is really nothing more than what you've done probably around 8th to 10th grade, give or take. The difference is now, rather than giving you the number as 7, I'm now writing it as a sum and goes from 1 to n of a little xn squared. Fine. But in principle, it's the same thing. And so I can now try to write this as something in more of a matrix form. So let's see. This is good? Excellent. Thank you. It's going up. I feel like R2D2 is in the class right now and he's having fun. All right. There we go. All right. Thank you, D2. All right. So now we would get the sum, n goes from 1 to n of xn squared times a, plus the sum, n goes from 1 to n of xn times b, is the sum, n goes from 1 to n of xn yn. That's the first equation. And the second is the sum, n goes from 1 to n of xn times a, plus the sum, n goes from 1 to n of 1 times b, is the sum, n goes from 1 to n of yn. Well, for those of you who like matrix notation, it's the sum of xn squared, the sum of xn, the sum of xn, the sum of 1, acting on a and b, equals the sum of xn yn, the sum of yn. 2 equations, 2 unknowns. Should there be a solution? Will there always be a solution? but most of the time there will. And I'm not going to write it down, but you get formulas A equals blah and B equals blah. The formulas are in the handouts. All we have to do is solve. If you want, you can solve for one in terms of the other, substitute, plug and check. If you know a little bit of matrix notation, you can take the inverse of this matrix. So as long as the matrix is invertible, you will have a solution. So what I want to do now is I want to give you a brief idea of what you need to do for this not to be solvable. As long as you don't do one thing of incredible stupidity, it will always have a solution. And it really is incredible stupidity. You have to work really hard to do this. Right? Imagine you want to see, I know some people are thinking, oh my God, I'm going to be real. No, trust me, you'll be fine. You want to see, does it take more or less time? How does the time take for a ball to roll down an inclined plane vary with the angle? Anybody do this experiment in physics? Right. So if you want to try to figure out how the time to roll down depends on the angle, what will you do? How will you gather your data? Okay, perfect. So as long as you do that, you are fine and you will never make a mistake. The only way you will make a mistake is if you do not vary the angle. I want to see how time depends on the angle, and I'm only going to measure things at one angle. And then I'm going to try to find the best fit line. You do that, and not surprisingly, things will go to hell. Because you're not varying your angle. So as long as all the xn's aren't the same, it will always be invertible. How many of you know some probability? If you know some probability, what the determinant of this matrix is, which tells you if it's invertible, it's the variance of the data x1, x2, x3 through xn, where you put a massive size 1 over n at each x. The determinant is the variance. And as long as the data points aren't all the same, the variance is positive, the matrix is invertible. If all the data were the same, let's say every value is equal to 5, then this is 1, this is 5 times n, this is 5 times n, and this is 5 times 5 times n. So the top row is 5 times the bottom row. So if all the data points are the same, it turns out that the matrix is going to be degenerate. The first row is a multiple of the second row. You will not get a solution. But you should not be trying to use the method of least squares in a situation where you're not varying the x's. I want to see how y changes with x, but I'm not going to change x. Okay? So as long as you don't do that, you're fine. All right. So let's talk a little bit now about the consequences. This is terrific. It allows us to find the best fit values of A and B, but this only lets us work with linear relationships. So the question is, how restrictive is this? Well, let's see where we needed to use the linearity. The real point, and we'll see how well this moves, is that when we were over here, when we differentiated this with respect to A and B, what we wanted to do was to have the resulting expressions depend linearly on A and B. So when we got over here to our equations, it only depends on A to the first power, only depends on B to the first power. That's really nice. So I actually do not need to be looking at a polynomial that's linear, y equals ax plus b. I need to look at polynomials, or more generally, combinations of functions that depend linearly on the unknowns. Looks like it's going up, so let's try to make it go down. So somewhere through here. All right. So imagine I now have y is like
It went back up.
But am I still in focus? So let's say I would say y equals a1 f1 of x plus ak fk of x. So now I have a situation like this. It still depends linearly on the unknowns a1 through ak, but I'm allowing myself to have any dependence on the x's that I want. All that would change is rather than having an xn come down, I might have an xn squared, or an e to the xn, or a log of xn, or a sine of xn. None of that really matters. So I can greatly expand what I can apply the method of least squares to. It doesn't have to be linear. It only has to be linear in the unknowns. So let's go back to gravity. So force is g m1 m2 over r squared. So maybe we believe that force should be proportional, I'll do it like this, to r to some power. Can we use the method of least squares, with my unknown parameters k and p? And if not, which parameter is causing trouble, k or p? Any thoughts as to, yes, p is causing trouble. If I take the derivative with respect to k, I just get r to the p. Perfect. It's linear in k. In fact, k doesn't even appear. But if I look at the other one, oh, this is going to be painful. R to the p is e to the p log r. So if I take the derivative, I will get a log of r times e to the p log r, or just the log of r times r to the p. This is not linear in p. And in fact, if I take the derivative with respect to k, I have an r to the p floating around. That's not linear in the p as well. So even though it's fine with k, it's not fine with p. P occurs in a fundamentally bad way, that the method of least squares will not work. So if this is the case, it means the method of least squares is unfortunately restricted enormously in terms of where we can apply it. There is a change of variables we could do, however, that would fix this. What could we apply to both sides? We've done this many times already. So how should we view the data? What should we do to both sides? Take a log of both sides. Excellent. So, again, in your toolbox of things to try, take the logs of both sides. Have I given you I teach differential equations like I have a young baby lecture? When I taught differential equations here, my daughter Kayla had just been born. And when you have a young baby, the baby is crying. You don't know necessarily why the baby is crying, so you go through a list of things to try. Does the baby want to be fed? Does the baby want to be held? Does the baby want to watch the Red Sox? You just keep going down the list until you find something that calms the baby down. When you have data, you should always try, let me do a semi-log plot, let me take the log of one side, let me do a log-log plot, let me take the log of both. Does that make the data look better? Does it illuminate relationships? This should now just be a go-to thing you always try. If I take the logs, I get the log of f is the log of k plus p log r. Oh, so this is the same as y equals ax plus b, where now the role of y today will be played by the log of f, the role of x will be played by the log of r, the role of a will be played by p, and the role of b will be played by the log of k. And so if I do this, yes? Because I have k r to the p. I'm not doing r to the negative p. So if I take the log of both sides, the log of a product is the sum of the logs. So I get the log of k plus the log of r to the p. And then the log of r to the p is just p log r. So I'm using the log of a product is the sum of the logs. So we can now apply the method of least squares. At the end of the day, we'll get the value of a. Great, that's p. And we'll get the value of b. That's the log of k. All right, I can hit the exponential function on my computer. Not a big deal. So the point of this is that the method of least squares is enormously more practical than it initially looked. I can look at combinations like this, and if I have some parameters that are unknown, often by doing the log change of variables, I'm okay. All right. So now we're going to go back to presentation. Is it somewhat in focus? Okay, so using our method of least squares, we got a value of 4.99 and 0.48. So I'd say a value of b is significantly off. The value of a is damn good. If we use the absolute values, if we use method 2, then the best fit value of a is 5.03, and the best fit value of b is less than 10 to the negative 10 in absolute value. For this problem, absolute values did a better job. But we don't have the ability to have these closed form expressions. And so it's just worth Really being aware of the advantages and disadvantages of the various techniques. In statistics, they are really big on linear regression. But one of the problems also with linear regression is that it is worse to have one error of size 2 and one error of size 0 than to have two errors of size 1. Even though the total error is the same, errors get magnified when you square. And so you are very sensitive to one or two bad data points. One or two bad data points can really drive the values of your best fit parameters. They are not nearly as impactful when you do absolute values. Right. How many of you have heard of Zipf's law? Excellent. This is something that occurs in a lot of different situations. So these are the 25 most populous cities. I have not bothered to modify the slides from when I lectured in 2014, the last time I taught this class. So when I say I believe this is from a few years ago, I now know it's from a few years ago. Right? The question is how many years ago? And of course, when you talk about cities, what do you mean by city? Do you mean the metropolitan region? Do you mean or the city proper? Based on these numbers, it's not the metropolitan region, because the largest American city is not only 8.3 million people for metropolitan area. So here is a plot of the rank of the city population versus the number of people. Can anybody sniff out a relationship by looking at this? I can't. What should we do? What should we do to the data? Take logs. So I'm first going to just plot the rank versus the log of the population. Doesn't really show much. Now I do the log of the rank versus the log of the population. And all of a sudden we see an interesting relationship between American city sizes. And again, this is one of my goals in the course. I can give you formulas to memorize and we can do all this, and you're going to forget most of them and you're never going to use most of them in the rest of your life. I really want to focus on ways to look at problems and things that you can use once you leave this, either in other classes or later in life. There's a relationship, it seems, between city rank and population. So here is a plot of the 100 most populous cities. Here's a log-log plot. And again, you see an incredible fit. So this is the power of the method of least squares. I want to talk briefly now about some work I have done recently for the school districts. So for about 50 years, Williamstown and Lanesboro have shared a middle high school. And each town has had their own elementary school. We've had 3 school districts and 4 school committees for the 3 buildings. Yes, we actually had more school committees than buildings. It's involved. We've decided to try to fully regionalize, and there are advantages to it, but there's also disadvantages. And there are concerns, not necessarily the same concerns in each town, about what would happen if we had just one school committee for the 2 towns. One of the big issues is maintaining local control of your elementary school. Each town wants control of their elementary school. The school budget for the 2 towns is on the order of $21 million. We get about $3.5 million a year in something called Chapter 78 from the Commonwealth of Massachusetts. $3.5 million is not peanuts relative to our school budget. It's very important to know how that money should be divided among the 3 schools. So right now, we have voted to regionalize, and we are now one school district. Because we are one district, the Commonwealth will no longer tell us how much money goes to each school. They will just tell us the lump sum that the state will give our district. Before, we knew how much money went to each school. What we would like to do is figure out how much money would have gone to each school if we were still 3 different districts. If we use the standard way the state does to calculate things, it would cost Williamstown $360,000 approximately to have the same level of service if we regionalize, and Lanesboro would save $480,000. So the district as a whole would save $120,000, but it seems a little bit strange that if you save $120,000, one town gets almost $500,000 and the other town loses $360,000. That when more money is coming in, one of the towns is worse off. Any economics people here? Do you know what phrase you would use for a solution like this? Have you hit Pareto optimal? All right. So you want to be in a situation where nobody's going to be worse off than before. And so it was very important that we find a way to fix this. And we were told, unfortunately, that this is just the way the laws of Massachusetts are. We can't do anything about this. There are so many advantages over regionalization. We're sharing by sharing a superintendent and savings for all these other things. It's still a net plus for towns. It's just not as much of a plus as it could have been. Well, I will be blunt. I'm a mathematician. This is one of the few times I should be valuable to my committee members. Look, let me take a look at this. And so I tried to use the method of least squares to find a way to estimate what the Commonwealth would have done. And so there were three things I wanted. I wanted a fair formula that predicts well. I wanted the formula to be transparent. I wanted it to be easily explained. And I'm happy to say more after we have a mechanical malfunction. So using the method of least squares in linear regression, I used the following as my data. The populations of the three schools and how much property value the assessments of the two towns. So this formula over here, here the beta, think of that as your A and your B. These are your best fit parameters. I now just have 5 of them. Or no, I'm sorry, I have 3. The percent that goes to each school. And then the Y's, this is my observed data. The X's are the observed data. This is using our techniques to find the best fit answer. So what properties do we want the solution to have? We want it to exist. We want the values to be between 0 and 1. We want it to be stable under small changes. And we want the sum to be 100%. We want to divide all the money to the 3 schools. We don't want to leave any money on the table. And we don't want to try to divide more money than we're getting. And so here is a plot of historic data going back to 2007. If you look, things are fairly stable in terms of from one year to the next. And so I predicted 2018 based on the data from the first 10 years, or the last 10 years. So these were the percents I predicted for each of the 3 schools. These were the actual observed, and this was the error. So I predicted Lanesboro, for instance, elementary should have gone in 21.78. They actually got 22.02 according to my formula. I'm sorry, they should have gone in 22.02 according to the state formula. So we were off by about 0.24%. So how bad is it to be off by 0.24%? Well, if I'm trying to launch a rocket to the moon, and I'm off by that much, because the distance is so great, probably we'll miss the moon. For $3.5 million, 1% is about $35,000, 0.3% is about $10,000. So we're off by about $10,000 per school out of about $3.5 million. And we're saving $120,000. So the amount that we're off by, and again, the formula is never going to be perfect, it's small enough that it is well within the range that we are very comfortable with what's going on. So this is a great application of the method of least squares. And while I doubt any of you are going to be on a school committee in the very near future, you might someday, or you might want a job over the summer where you're working for a company and you want to be able to do some basic data analysis. You've got the tools now to do some basic analysis, to collect some data and try to sniff out a relationship. And it's amazing how many people do not know to conduct analyses like this. All right, I'm going to switch back now to word counts. So I'm looking at a plot of rank versus occurrences of some of the most common words in the English language. What should we do to make this data more understandable? Take the log, right? Sure. Yes, okay, good. So if we take the logarithm, you can see that the word count frequency and the rank beautifully linear under a log-log plot. So I really want to drive home the point that when you have data, think log-log. You can sniff out relationships that might not be there otherwise, and techniques that might initially seem restricted or limited are now much more powerful. All right, so I'm going to turn this off now if I can.